All right, so today, we're not just talking about chemistry. We're actually tracing the lineage of a really powerful chemical family. Think of it like this. We're going to meet a parent compound and its two most important children, and we'll see how their relationships literally build the world around us, from the sting of an ant all the way to the scent of a flower. This is going to be fun.
So let's kick things off with a little bit of a mystery. What in the world could possibly connect the sharp, tangy bite of vinegar with, the slick, cleansing power of a bar of soap? I mean, on the surface, they seem like they're from completely different worlds, but deep down, they actually share a secret chemical ancestry.
And the key to solving that mystery is exactly what we're diving into today. The answer is found inside a single, incredibly versatile family of organic compounds, and the wild part is that they all spring from one fundamental building block. To really get a handle on this family, we have to go right to the heart of their world, to the one piece of architecture that defines every single one of them.
And here it is, the carbonyl group. It's pretty elegant in its simplicity. Just a carbon atom sharing a double bond with an oxygen atom. The best way to think about this C double bond O structure is like the shared family DNA. If you see this, you know you're in the right neighborhood.
Now this is where it gets interesting. What happens when you take that carbonyl group and you just attach what's called a hydroxyl group, that's an OH? Well, bam! You get the carboxyl group, which we write as -COH. This little group is the official signature of the head of our chemical family, the parent compound itself.
This chart just lays it all out perfectly. Take a look at that first column. That's our parent, the carboxylic acid, with its defining COOH group. Okay, now look at its two main derivatives. In the middle, you've got the ester, where some carbon group, which we just represent with an R, replaces the hydrogen on that OH. And then over on the right, you have the amide, where the entire OH group gets swapped out for a nitrogen-based group. See the pattern? It's all about just swapping out one tiny piece attached to that central carbonyl carbon.
All right, it's time for a more formal introduction. Let's get to know the head of the family, the compound that kicks this whole thing off, the carboxylic acid.
I guarantee you have met these before, probably without even realizing it. Acetic acid? Yeah, that's what gives vinegar its famous kick. And formic acid is what makes an ant sting, sting. These are what we call aliphatic acids, meaning their carbon atoms are linked up in open chains. But you also have aromatic versions, where the carbons form a really stable ring structure, like benzoic acid, which you'll often find used as a food preservative. Seriously, they're everywhere.
So, now for the really cool part. How does this family actually expand? How do we create the children, the esters, and the amides from that parent acid? Well, this is where the magic of chemistry comes in, and we get to see how the family tree branches out.
Making an ester, a process we call esterification, is kind of like following a simple chemical recipe. You just take your carboxylic acid, react it with an alcohol, and then you add a drop of a strong acid to act as a catalyst, just to get things moving. And the result? The OH from the acid and an H from the alcohol, they combine and they leave as a water molecule, which lets the two bigger pieces link up, and boom, you formed your new ester. It's a really elegant swap.
And guess what? Creating an amide follows a strikingly similar script. This time, instead of an alcohol, you react the parent acid with ammonia or a related nitrogen compound. Add a little bit of heat, and once again, that hydroxyl group is replaced, this time by the nitrogen group, forming the amide. The key takeaway here is this predictable pattern of substitution. It's what gives chemists such incredible power. Okay, so we're building all these new, but really similar compounds. Things could get confusing fast. So how do chemists keep track of who's who in this growing family? Well, they use a very clever and logical naming system. Let's take a look at how it works.
Broadly speaking, there are two approaches. On one hand, you have the common names, which are often like historical nicknames. For instance, formic acid comes from formica, which is the Latin word for ant. Makes sense, right? But on the other hand, you have the IUPAC system, which is like a universal language for chemistry. An IUPAC name is basically a blueprint that tells any chemist anywhere in the world the exact structure of the molecule they're looking at.
So the most important thing about the IUPAC system isn't about memorizing every single rule, but really just appreciating its logic. It's a simple idea. Find the main carbon chain, number it starting from that key functional group, and then just systematically name any branches that are hanging off. It turns naming from a history lesson into a clear, repeatable process that just gets rid of all the ambiguity.
So we've seen how to build the family, but chemistry is a two-way street. What about taking it all apart? This process is called hydrolysis, which literally means splitting with water, and it's how we can travel right back up the family tree.
Now this is where it gets really cool. As you can see here, you can break an ester in two different ways. On the left, if you use an acid, you perfectly reverse the creation reaction, and you get your original carboxylic acid and alcohol right back. But over on the right, if you use a base instead, something different happens. You still get the alcohol, but the acid gets converted into its salt form, which is called a carboxylate salt.
In that process, the base hydrolysis of an ester, it has a special, really famous name, saponification. And this right here is the solution to our mystery. Fats and oils are just giant, naturally occurring esters. So when you heat them with a base, like lye, you're performing this exact reaction. And that carboxylate salt that you produce, that's soak. That's how it's made.
And amides? Well, you guessed it. They follow the exact same predictable logic. You can split them with either an acid or a base. Just like we saw with the esters, using an acid gives you back the parent carboxylic acid, while using a base gives you that carboxylate salt. This brilliant consistency is what makes this family's chemistry so reliable and just so useful.
So, we've seen this incredible family grow and shrink through a set of really reliable, predictable rules. And this leads us to the big question. If chemists can so precisely swap out one small part of a molecule to turn an acid into a sweet-smelling ester or an oil into a bar of soap, what does that incredible level of control mean for the future? For designing new polymers, smarter drugs, and more advanced materials? That power of predictable transformation, that is exactly why this family is one of the most important in all of chemistry.